Lecture-3.5 of your book. We've talked about this. This is an application that you can go through on your own. We talked about this, changing coordinates. We talked about the transition matrix, and let's discuss this a bit. So this is the idea of going from a standard basis to two different non-standard bases. To go from a non-standard basis to a standard basis is easy. You just find the transition matrix V. If you want to go from a standard basis to a non-standard basis, first you need to find the transition matrix that takes you from this basis to this, and then if you find the inverse of that matrix will take you from the standard basis to the non-standard basis. And of course, if you want to go directly from a non-standard basis to another non-standard basis, you first go here to here and then go here to here, which means you multiply with V first and then you multiply with U inverse, and that's how you can go directly from a non-standard basis to another non-standard basis. Now let's talk about the change of basis for a general vector space. This is the idea that if you have a vector space V and you have a basis for it, let's call that collection E. So E is a basis for my vector space V, and V1 to Vn are the basis vectors in this collection. Let's take any V in this vector space, small v. This is a vector in this vector space, and recall that this vector space can be anything. It can be a vector space of n. It could be Rn, it could be R3, it could be a vector space of functions, it could be a vector space of matrices, it could be a vector space of polynomials. So this is a general vector space now. We're not limiting ourselves to just vectors in R2 or R3 or Rn. We're talking about a general case here. And so the idea is, if this is a basis set, then you can express V as, of course, as C1, V1, C2, V2. And because V, we're making V to be an n-dimensional space, so you need only n vectors. So V1 to Vn will do the job for us. And these scalars C1, C2, Cn, these are the coordinates. You can make another vector and a vector in Rn such as this, which you can populate by C1, C2. So V1, V2 and Vn may not be in Rn, but now C1, C2 up until Cn are in Rn, which is an n-dimensional space. And let's make a vector C up until C1, C2 up until Cn, and now you've created a vector C, and we call this vector C the coordinate vector of V with respect to E, and we denote it in this bracket notation. So V was your vector, and the coordinates of this vector are now with respect to the basis E. So this is how you write a coordinate vector, and CIs are called the coordinates of V. We've already seen this in case of a two-dimensional case, but now we're generalizing this a bit. Okay, so if V is an n-dimensional vector space, then it is possible to change from one basis to another by means of a transition matrix, which means even if these vectors were polynomials or matrices or anything, you can still use the idea of a transition matrix, because coordinates, let's show that idea a bit in detail. The idea, and so let's demonstrate this idea. The idea is, even if, let's suppose, I was working with a vector which was, perhaps I was working with some polynomials. I was working with, let's call this vector V as 1x plus 2x squared plus 3x cubed. And so I'm in the space P3, or rather P4, which is the space of polynomials of degree less than n, which is less than 4. So 3-dimensional up until degree 3 polynomials. And so notice that this is just, if I make a basis vector, the standard basis for polynomials would be as follows: 1 x, x squared, and x cubed. This would be the standard basis for this. Let's not call it P4, let's call it E. So this is a standard basis for this polynomial space. This of course is not the same as Rn, but if I take these coordinates, now I can express, if I express the coordinates of V with respect to E, then that's just the coordinate vector C1, C2, C3, C4 in the representation V equals C1 times the first vector V1 plus C2 times the second vector, which is x, plus C3 times the third vector, which is x squared, and C4 times the last vector, x cubed. And if you notice, you can already compare these two representations. You can see if I set C1 to be equals to 0, C2 as 1, C3 as 2, and C4 as 3, then I will just get x plus 2x squared plus 3x cubed. So these are the coordinates with respect to this standard basis. And so the coordinate vector V with respect to E would just be 0, 1, 2, 3. And now notice that this coordinate vector is in R4. Now let's suppose I had the representation of V in some other basis. For example, I could represent V as alpha 1 V1 plus alpha 2 V2 plus alpha 3 V3 plus alpha 4 V4, where these were, of course, they have to be polynomials now. But alpha 1, alpha 2, alpha 3, alpha 4, again, these are just coordinates, and I can write V with respect to f. The coordinates would be just alpha 1, alpha 2, alpha 3, and alpha 4. And this would still be in R4. And so recall that if I want to go from one coordinate to another coordinate, let's call this x, and let's call this c. So if I want to switch between two coordinates, I can still write an equation of the form x is equals to uc, where c is just this. C is in R4, x is in R4. Perhaps if I write transpose here, this would be more precise. And u is just now n by n, which is basically a 4 by 4 matrix. And it's a 4 by 4 transition matrix that will take coordinates of c to x. Of course, I have to find this u first, and we can do that in a bit. But all of this I did to represent just the idea that we're now talking about a general vector space. We are talking about polynomials now. These can be functions, these can be matrices, whatever have you. And you can apply the same idea of a transition matrix because the coordinates themselves will be in Rn. So perhaps I can say something like following: in an n-dimensional space, the transition matrix is an n by n matrix, right? And something similar to that I've already written in these notes. So if V is an n-dimensional vector space, then it is possible to change from one basis to another by means of a transition matrix. And another claim that this matrix is necessarily non-singular. That is, you will always have an inverse of this matrix. Let's do an example. Let E equals to W1 to Wn. This is a basis. And F is equals to V1 to Vn. another basis. So E is a basis for V, F is a basis for V. Now notice that if both of them are basis vectors, I can do the following. I can represent W1. W1 is just a vector I can do the following. I have a collection E that is W1 up until Wn, and I have a collection F that contains V1 up until Vn. This is a collection of basis vectors and this is a collection of basis vectors. And the idea is, if this is a collection of basis vectors for the vector space V, then W1 is a member of V. In fact, all Wi's are members of V, and in fact all Vi's are members of V. And recall that if you have a basis, then if I say that something is a basis, then any element for a basis, then for all V's in my vector space, this V is different from these Vi's, don't confuse it with this, I can always write V as a linear combination of the basis vectors, which means I can write W1 as a linear combination of V1 to Vn. I can write W2 as a linear combination of V1 to Vn, and that's exactly what's been done here. W1 has been written as a linear combination of V1 to Vn. W2 has been written as a linear combination of V1 to Vn. And notice these coefficients. These coefficients are just the scalars needed for this linear combination. V1 to Vn are vectors, and S11 to S1n, these are all scalars. Now let's suppose we have some representation of a vector V. So let's suppose V, I'm not going to write this down, these are already written, blah 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 up until Wn, blah blah blah. Let's suppose we have a vector V and I have some representation of it. I can write V, I have some coordinate representation of it, that is, I am saying that this is basically x1, x2 up until xn. So these are the coordinates of V under the basis E. And so I want to switch from this E basis, which was W1 to Wn, and I want to switch to V1 up until Vn. And let's see how we can do that. Let's note first of all that V, if there is a representation of V with respect to E, then I can just write x1 W1 plus x2 W2 up until xn Wn. This was the representation of V in terms of the basis vectors in E. Now since I have represented every vector W1 in terms of these standard basis, the other collection V1, V2, Vn, I can replace each W1 or Wi with the corresponding collection here, linear combination here. So if I write this down explicitly, what will it be? Let's say I write x1 and I replace W1 with S11 V1 plus S21 V2 up until Sn1 Vn. This was just the first term in this linear combination. This is the first term in this combination. I of course need to write down the rest of the terms. x2 s12 v1 plus s22 v2 up until sn2 vn. Alright, and so I can continue this process. Up until xn and write down all of these linear combinations. s1n v1 plus s2n v2 plus up until snn vn. Okay, and so this entire thing is just v represented now in terms of v1 to vn, and we can make it a bit neater by collecting all of the terms in v1. If I collect all of these terms, let's suppose I want to collect all of this is addition happening, and so I can just add these terms together and I can write them in a nice summation notation. I can write this entire thing as summation s, notice the index 1j, vj, xj, because these were the x1, x2 up until xn, and all of them are being multiplied with the same vector v1. So v1 over here. This is the scalar we need. It's a summation of j terms. J goes from 1 to n, and I can write the next term again, and I repeat the same process with these terms. If I repeat it, then that becomes summation j goes from 1 to n s 2j xj and v2, and the remaining terms can be written exactly like that, and the last one will be just vn and some scalar written in the summation form, right? So what have we done? Let's look at the result. The result is basically, if I call all of these, now let's name these. Let's name this y1, let's name this y2, and let's name all of them up until yn. Then what I've done is I have v as y1 v1 plus y2 v2 up until yn vn, where notice that I have switched from coordinate basis w1 to wn to the coordinate basis v1 to vn. This one right here, v1 to vn. And now I can say that y is actually the representation of v in terms of the coordinate basis collection f, where y is nothing but this coordinate vector y1 to yn transpose, and x was x1 to xn transpose. And what does that give us? Let's go back. It gives us this, the following, that now each yi is this summation term, and if you expand it into a matrix vector product, you can write this down as a matrix, because this is just a summation going from 1 to n for each yi. Then you can view it. Perhaps I can show you how to view this as a matrix vector product. Let's write this down. So each yi is summation sij xj, j goes from 1 to n. So if I write this down as y1, y2 up until yn, then I have the following. This entire thing is nothing but summation s1j xj. This is summation, the second line. So this is the first line, this is the second line. This is nothing but summation s2j xj. And this last one is summation snj xj. And now if I write this down in terms of matrices, if I separate all of these terms, x1, x2 up until xn, the first row that I will have is s1. So for yi, I can write this as s12, s11, s12 up until s1n, s21, s22 up until s2n, and sn1, sn2 up until snn. And if I try to multiply this matrix S with this vector x, notice that when x1 is being multiplied, x1 will be multiplied with s11, s21 up until sn1, exactly what we need for each of these y1s, y2 and yns. Notice that when y is 1, you still have to go through each of these j's. So y1 is a sum of some scalar being multiplied to each of the xj's and then adding them up all together. And so this is the matrix. You can multiply this whole thing and check that this and this is just the same thing. And I highly recommend that you do that so you understand what's going on much better. Okay, so what I've done is we've now been able to write y as s times x, where s was the transition matrix. So there you go, that's the transition matrix. And moving on, the idea is again that s has to be non-singular. Why is s non-singular? Let's check this. So y is now equals to sx. Y, if we see that we're calling y as the transition matrix, what we're basically saying that if I can go from coordinates x to coordinates y, then I'm basically expressing each vector x1 w1 plus x2 w2 up until xn wn as equals to y1 v1 plus y2 v2 plus up until yn vn. That's what we're doing. That when coordinates x change to coordinate y, we change bases from w's to v's. And so if y equals to sx, this is an if and only if condition. This I don't have to prove. You can see that the way we've defined this entire thing, this implication, this by implication holds by definition. And so what do I need to do? Let's check what happens. If I want to check that s is non-singular, I can do the following. To check that s is non-singular, we set y equals to 0. When I set y equals to 0, I have the equation sx equals to 0. So let y be the 0 vector. This tells me that sx is equals to 0. It also tells me that this entire thing, x1 w1, so let's separate this, x1 w1 plus x2 w2 up until xn wn. This is also equals to each of the y's are 0, so this has to be the 0 vector. I know from the start that wi's were basis vectors, which means they're linearly independent. If they're linearly independent, then I know that for a linearly independent set, this entire thing is 0 if and only if all xi's are equals to 0. This is just coming from the definition of linear independence. They're all linearly independent, then this equation just has the trivial solution. If all xi's are 0, that means in this equation over here, I have xi's equals to 0. That means x is the 0 vector. In other words, I am saying that Sx equals to 0 only has trivial solutions. And if you recall, that's an equivalent condition to saying that S is a non-singular matrix. So both of these conditions, once you set y equals to 0, you see that because of the linear independence of wi's, you get all xi's to be 0, and therefore this equation gets, the homogeneous equation gets a trivial solution, and therefore you can conclude that S has to be a non-singular matrix. So if S is a transition matrix from coordinates x to coordinates y, S has to be a non-singular matrix. And that's this part of the proof. And so if this is non-singular, what does this tell you? It tells you can find the inverse. And so the inverse exists, and now you can go from coordinates vector y's to coordinate vectors x as well. So you can go both ways. You can go from this basis collection to this representation, or this representation back into this representation. This representation to this representation, and back and forth. You can switch using this matrix S. Okay, let's go on. Okay, and here's an example that uses these ideas for polynomials. They're in P3. Suppose that in P3 we want to change from the ordered basis, the standard basis, to this different basis. And the idea is simple. You first try to represent, let's open these two together. So we follow the same ideas. But first we find a representation of the basis vectors in terms of the other basis vectors. So if I want to go from this representation to this representation, what we do is express each of these vectors in terms of these vectors, and that's easy. 1 can be simply written as 1 times 1 plus 0 plus 0x plus 0x squared. 2x can be written as just 0 times 1, 2 times x plus 0 times x squared. 4x squared minus 2 can be just written as minus 2 times 1 plus 0x plus 4x squared. And now the transition matrix is immediately available by taking these coefficients. The coefficient over here was 1, 0 and 0, and that makes your first column 1, 0, 0. Then you take the second collection 0, 2, 0, that makes your second column, and the third representation minus 2, 0, 4, that makes your third column. So if you recall, what we're essentially doing, if I jog your memory a bit, when we were making U was just made by these, where is it, yeah, right over here. So when we expressed U1 and U2 as 3E1 plus 2 and 1E1 and 1, we just put 3, 2 in the first column and 1, 1 in the second column to find the transition matrix. And that idea holds true for this one as well. So these are the columns, and now that you have a 3 by 3 matrix, you can find its inverse. Please don't try to use Cramer's rule. Use Gaussian elimination, augment it with an identity matrix, and then use Gaussian elimination to find the inverse. And once you have the inverse, you can represent any vector. If you have a plus bx plus cx squared in P3, you can represent it in terms of these three basis vectors by using this equation. and this equation is nothing but S inverse of y equals x. You can go through this example and it's the same thing. Okay, and lastly, here is another flip side to this entire discussion. Initially we started by talking about transition matrix and how a transition matrix is non-singular. Now we flip that argument and we say every non-singular matrix is actually a transition matrix. That is, any non-singular matrix can be thought of as a transition matrix. So if you make a matrix S, and if it is non-singular, then it has some linearly independent columns, and those columns are basically the basis vectors that you're switching from. And you can read this discussion. This is a similar discussion. I recommend that you go through this on your own. If you don't understand it, I will go through it again and discuss this, but this is a key idea that you should understand, and I'm leaving it up to you to go through this on your own.